Okay, so this is section 2.1, rates of change in limits, and some of the stuff that you're going to see in this lesson you may have seen last year in pre-calc, and if it seems new to you, that's okay too. So we're going to start off by defining a limit. Okay, so limit is a number that something approaches as something else gets closer and closer to a specified number. Let's break this down a little bit more. A limit is really a y value, and that y value is determined by seeing what happens to a function as x gets closer and closer to a specified number. So a limit overall is really a y value. So the shorthand notation for this, we're going to say the limit as x approaches a number, and we're going to call that number c for right now. But this is an incomplete statement, and last year if you took pre-calc and your teacher made you write f of x or an actual equation in here over and over and you wind every step of the way, it's really needed until you actually evaluate a limit. So you need to know what you are taking the limit of, which function that is. So in this case, we're going to say the limit as x approaches c of the function f of x. So again, this is the number that x is approaching. This over here, this f of x, this is the argument of the limit. In order for a limit to exist, the left and right hand sides must match. And anytime you take a look at a limit, whether it's graphically or any other form, whether it's algebraic, as long as the left and right hand side match each other, then the limit itself exists. To talk about a limit from the left, or the left hand limit, you're going to say that x approaches a number, and then you're going to put a little superscript with a negative, and that's telling you from the left. Again, you have to have the argument there. So the limit as x approaches c from the left of f of x, that's the left-hand limit. When you talk about the right-hand limit, the only thing that changes in the expression, as you can imagine, is the superscript. So now we're talking about c from the right. Argument is still there. So that would be for the right-hand limit notation. So again, the only way for a limit itself to exist is if those two things equal each other. Okay, now something that's I'm going to kind of point out here is the word approaches, because the limit only depends on what happens as x approaches a number c. And we're going to see a couple of examples of when the function is defined and when it's not defined at c. So it just depends what happens as the function as x approaches a value c, not what actually happens at c. So I think I've repeated myself a couple times there, but let's go ahead and take a look at 3 ways to find the limits. In calculus, we're going to look at these 3 ways for almost every type of problem that we do. Graphically is by looking, of course, at a graph. Numerically is looking at data specifically using either tables or specific points. And then analytically is when we're given a function and we manipulate it somehow. So we're going to start off with the graphical approach for limits. I call this approach hide and seek, and you'll see why in just a second. But there's a couple things I need to point out first. When you are taking a look at a limit and when it asks you to find something, first direct your attention to what value x is approaching. Is it a constant or is it something else? So in this case, it's a constant, and that constant is -4. Notice the superscript here is negative, so this means this wants to know the limit as x approaches -4 from the left. This wants to know the value, the limit as x approaches -4 from the right. This just wants to know the limit as x approaches -4, so we'll see how to get to that in just a second. Anytime you're talking about a limit itself, we care about what happens as we approach, not what happens at that value. So the first thing I'm going to do is I'm going to kind of put a little blinder on here, and I'm going to hide what happens at the graph. Now you can do this with your pen. You can just hold it vertically and cover it up. But you will notice that this is at the value of x equals -1, 2, 3, and 4. So here's the values of x equals -4. This entire vertical area is going to be x equals -4. So when we look at this first expression here, this first limit, it's asking you to evaluate from the left. So what that means is you want to take all the values here that are to the left of negative 4, and you want to approach negative 4 from this side. So we're actually going to be moving to, we're actually going to be moving to the right. Okay, I fight with the iPad sometimes, so just bear with me. So we're going to be approaching it from the left, so we're moving to the right. Now as we approach these x equals negative 4 values, we want to know what's going on with the function itself, with the y values. So I'm just going to follow along the function, and I'm going to get to this point, and I'm going to ask myself, what value would I expect to see here? If this red strip wasn't there, what would you expect? And if you take a look, you would expect a point right there, and that y value is a positive 4. So that would be the limit of the function as x approaches negative 4 from the left. You can see as you take a look at this next limit and you approach the function, you approach x equals negative 4 from the right, you're going to have the same value. Because I'm following this function, the x values are getting closer and closer to negative 4 from the right. What value would you expect? Again, you would expect a positive 4. Now, for the limit itself, when there's no superscript after the 4, this is saying what is the limit as x approaches negative 4. And to figure this out and to determine it, all you have to do is take a look at the left and right hand sides. Because they match, this function does have a limit there, and the value is just 4. Now, to take a look at an actual function value, which is what part D is asking us, it says, what is the function value at x equals negative 4? This wants to know the actual y coordinate point there, if there is one. So in order to do that, we're just going to have to delete the rectangle that I put in there and look at the y value. At x equals negative 4, if I go up to the function, there isn't one. So the function itself doesn't exist. So we just put a little DNE there. Now looking at this next graph, the first thing you want to take a look at is, again, what value is x approaching? And in this case, x is approaching positive 3. First from the right, then from the left, the overall value, and then the function value. Again, if it helps you to put your blinders on and kind of make a little hide-and-seek strip, I call it. And now take a look. As x approaches 3 from the right, here are the values of x that are bigger than 3. So as I approach from the right here, follow your graph. From the right, what y value would you expect to see? And I'm expecting a y value of 0. What y value would you expect if you approached x equals 3 from the left? And this one is different. We're getting a y value of 3 on this guy. So this graph is a little bit different than the previous one in the case where here I'm asking for the function's value, the limit, as x approaches 3 of the function. In part A and part B we got different values, and when that happens, the limit does not exist. And all you Mean Girl fans out there, the limit does not exist will make you happy. Yes. For part D, we need to delete that strip. So I'm going to go ahead and do that. And now we want to see what's going on at x equals 3. If I go to my graph, all of these values are x equals 3. Where does the function happen? It happens right here, and that is a y value of 3. So this is an example of where the limit didn't exist, but the function did. Whereas the previous example, the function itself didn't exist where we were looking at the limit, but the limit did. Okay, so we're on to page 2 now, but what I'm going to have you do is pause this presentation because I want you to try the next 2 examples on your own. And it's really important in calculus, actually in any math discipline, for you to try things on your own, because even if you make a mistake, then you learn from the mistakes that you're making, and then you won't make them on the quiz or on the test. So I'd rather have you make them now and just give it a shot. So go ahead and press pause and then come back. Okay, so let's take a look and see how you did. The first one is asking you to take a look at the limit as x approaches 6 from the left, and x approaches 6 from the right. For part C, it's going to ask you to take a look at the limit overall, and then for part D, it's going to ask you for the function value. So the first thing that I'm not going to be putting the rectangular strips up anymore, but if it helps you to cover up that vertical part at x equals 6, feel free to do so. But as you follow the function from the left as x approaches 6, I would expect to see a y value of -2. Additionally, if you do it from the right-hand side and you approach the x value of x equals 6, I again would expect a y value of -2. Because these two values match, the limit from the left, the limit from the right, there is an overall limit as x approaches 6, and that value is -2. Now, unlike the previous examples, at x equals 6, there is a function value, but it is not where the limit is. It's somewhere, it's disjointed, it's a separate point. And if I take a look at that value, that has a y value of +2. So this is just one of the examples in which case the limit value does not match the function value. So we're going to go ahead and take a look at the next example and see how you did on that one. Okay, now in this example we have a vertical asymptote occurring at x equals 0, and we're going to take a look at what happens to the function values as we approach 0 from the left first. And this graph, as it approaches that vertical asymptote from the left, is getting very, very negative. So the y values are getting infinitely large, but in the negative direction. So go with your gut instinct on this, and we're going to put down a -infinity. Now there's kind of a caveat with this, and infinity is not really a number, but we'll get into that in the next section. So for right now, let's just leave it be. The same from the right, the y values are getting infinitely large in the negative direction as you approach x equals 0 from the right, because the limit from the left equals the limit from the right. This thing does have an overall limit of -infinity as you approach x equals 0. The function value itself, though, does not exist because there's a vertical asymptote there. So double check your work, make sure you got the right answers, and if you didn't, just circle it and make sure you ask me in class tomorrow. And we're going to go ahead and move on now to a numerical approach where we find the limits through data tables. Okay, when you look at finding limits numerically, we're going to be looking at the data tables, and these data tables are going to get either generated by hand, or for the most part we're going to be using our graphing calculators. So if you don't have your graphing calculator, go ahead and press pause right now and go get it out. And what we're going to do is we're going to enter the function, the argument of this limit, which is right here. This is again the argument, what you are taking the limit of, with respect to, I should say, and we're going to plug that function into our y equals. Okay, so the biggest thing to remember here is that when you press the sign button on your calculator, it automatically gives you a left parentheses. We want to take the sign of x only, so make sure you close that parentheses and then go ahead and divide by that other x. So this is going to be in your y1 in your grapher. And what you're going to do is, we don't care about the graph of this thing. For right now, we're just looking at the numerical values. So the first thing that we have to do is look at our table, but before we can do that, we have to change the table. You're going to take a look at what value x is approaching, and that's where you want your table to start. Now we're going to move it around a little bit, but that's going to give us a good baseline for where we want it to start. So because x is approaching 0, you're going to go into your table by pressing second and then window, and it's going to give you these two options, the table start and the change of table. So the number that x is approaching is what you want your table start value to be. So in this example, table start is 0. The delta table is what you want x to increment by. Now we're going to select very, very small values for the increment because we want to know what's happening very close to the x value of 0 in this example. So we're going to go ahead and set our delta table to 0.001. And if you press table now, you're going to be able to go in and you should have something that starts at 0 and increments by 0.001, and you can just arrow up a couple of times so that you end up with a graph that, or a table that looks like this. So I'll give you a second, go ahead and press pause, or go back and listen to anything that you might have missed. I'm going to go ahead and insert my grapher screen right now. Okay, so I magically plopped in my grapher screen here, and the little note down here says make sure that you move your cursor onto the y value so that you can see the full decimals. And you'll notice if you don't do that, you see values of 1, 1, 1, error, 1, 1, 1. So it's not really showing the full picture, because if you cursor over, for example, on x equals negative 0.003, if you go over to the right and look at the y value, there's some more going on, but our calculator is going to go ahead and round it to the nearest, I think it's fifth decimal. So that's going to round it up to 1. The reason I call this hide and seek part 2 is, for argument's sake right now, I'm just going to put in what the calculator shows, but you would actually have, 0.9999, etc. Okay, but for right now, I'm just going to put the shorter version in because I'm going to save a little bit of time here. Additionally, this says error here. Now the reason I call this hide and seek is because exactly what you did with your graph, you're going to do with the data table. We want to know the limit as x approaches 0. So I'm going to cover up 0. I don't care what's happening to the function at that value. I care what's happening near that value. So in order for a limit to exist, the left and right hand sides must match. And if you look at this, if you approach x equals 0 from the left, meaning from values that are less than 0, you're getting y values of 1. If you approach it from the right, again, you're getting y values of 1. So this does have an overall limit of 1 for the y value. So I'm going to go ahead and write in that the limit as x approaches 0 of sine of x over x equals 1. Now we can confirm this graphically by taking a look at this guy, and it looks something a little bit like this. Okay, but this is the y value here of 1, and I apologize, it's not 100% accurate, but you get the idea. And again, if going back to what we did in the previous examples, if you approach it from the left and you approach it from the right, you're getting a y value out of 1. Now, for an extension, I would challenge you, go ahead and zoom in to the graph around this region here and see what's actually going on as you approach 0 closer and closer. And that can be, that we're going to be discussing that tomorrow as well. Okay, we're going to finish up today's lesson with one more example, and I'm going to have you try this one on your own. So press pause and then come on back when you're done. So hopefully when you entered this into your calculator, again, to get the absolute, you're going to go into math, and then you're going to arrow over to num for number, and you should see abs as your first choice. You need to close the parenthesis first, and then you'll be able to get the accurate graph and the accurate data table. So if you fill this in, you're going to get something that looks a little bit like this. Okay, so just like we did before, not all the limits are going to be as x approaches 0, but for these examples, that's what I chose. And here's an example of where the limit does not exist. If you take a look at your data table, as you approach x equals 0 from the left, you're getting a y value of negative 1 out. As you approach it from the right, you're getting a y value of positive 1 out. This limit does not exist. So overall, I like to write it over here, because if you guys want to use these notes, fold it in half, and then you'll be able to rework these problems without seeing all your work. So I always write the solutions on the right hand side. This limit does not exist. Now if we look at the graph of this thing, it's a little more clear as to why. It's very obvious actually. You've got an open circle here going that way, you've got an open circle here going this way. These are the y values of 1 and negative 1. And just like we did before, I can show you the hide and seek strip like that. And it's very obvious now as you approach from one side of x equals 0, you're getting a y value of -1. As you approach it from the other side, it's +1. That's why the limit does not exist. We're going to be focusing on the algebraic approach in the next lesson, but hopefully you have a better feel for graphical and numerical. So if you had any questions during this lesson, feel free to go back and listen to anything again. If it's still unclear, feel free to write a note down and make sure you ask me tomorrow.